we're going to add to each of these that we are going to graph as well. Oh, the practice questions for the last one were 3A and B, 4, 5, and 9. So now we're going to look at what happens with B values. And of course, from our first unit, remember that everything with the x's are liars. That 6 is actually a horizontal compression. We would multiply our x values by 1/6. So what is that going to do? That's going to change our x values. Again, we would have our regular coast graph, right? I'm going to draw out in, eventually you won't have to draw out the regular coast graph because it's going to be in your head. You'll just be like, I know what my coast graph looks like. I know it starts at a maximum, then goes center line, then minimum, then center line, then maximum. Here's my normal coast graph with my axes family. Now what's going to change when we multiply x values? Our axes family is going to change. In particular, we are going to look at this point, because at this point, we have reached one period. You see that when you do a horizontal compression, everything's going to get compressed, and your period is going to change. So on our new graph, I'm going to take that point 2 pi. I'm going to draw a different scale so it's not too squished. But can you see that if you multiply 2 pi by 1/6, and I'm not even going to reduce it, I'm just going to write 2 pi over 6. Does that make sense that that's where that green point, here I'll circle it in green as well. But if I did a horizontal compression by 1/6, that x value would change to 2 pi over 6. And this is how we're going to do the shortcut with horizontal compressions. Instead of, again, taking those 5 points and then drawing the arrows and saying I need to multiply all my x values by 1/6, we're going to notice the following. If you took one period, multiplied by 1/6 and get 2 pi over 6, this was separated into 4 equal sections by your axes family, it's still going to be broken up into 4 equal sections. And the mental math is not too bad. I'm going to label each of these 4 sections. I'm going to start with the one in the middle, because the one in the middle is exactly half of what's circled in green. Can you see if this is 2 pi over 6, exactly half of that would be 1 pi over 6? And then I'm going to do the very first ticky mark, because that very first ticky mark has to be half of pi over 6. Does that make sense that this then would be pi over 12? And then I do the third one, and the third one I do by counting. If one of them is pi over 12, does it make sense that the third one, and I'm not going to reduce this, would be 3 pi over 12s? If one ticky mark was 1 pi over 12, the third one would be 3 of them, 3 pi over 12s. I mean, that reduces to pi over 4. I could reduce the 2 pi over 6 to pi over 3, but we don't have to reduce fractions if we don't want to. We could leave it labeled like this. Now my y values are not changing, so this will still have 1 and -1, and maybe you can see from your a value is 1 that your amplitude would still be 1. So now we can graph. This is a coast graph. Coast graph starts at a maximum. And look how quickly we can draw our 5 points. We go from maximum, next ticky mark will be at center line, next ticky mark minimum, back to center line, back to maximum. We've completed one full period. But now our period is 2 pi over 6, whereas normally our period was 2 pi. So horizontal compressions, they are going to affect the period. So you have to somehow remember that B affects your period. However, you can remember that your B value affects your period. Or if you say it a little bit wrong, period, maybe you'll remember. So A affects the amplitude, B affects the period. And for all of these, we have to know what the original graph looks like to begin with. So in part B, we have y equals, and we have a tan graph, and we have tan of 2/3 x. X's are liars. This is going to be a horizontal stretch. You would multiply your x by the reciprocal, 3/2. If I label my axes family, and for the tan graph, normally we go one axis family into the negatives as well. We start with our tan graph by drawing asymptotes at all the axes families where things are not possible. So that would be pi over 2 and 3 pi over 2. And if you went in the negative direction, you would have negative pi over 2 as well. Then with your axes family, zero pi and 2 pi is where tan is equal to 0. It keeps on going forever. It's usually enough to draw only one section or two sections. Does it make sense that every section is actually one period? Because one period is how long it takes to repeat itself. So the period of tan period of y equals tan x, unlike sine x and cos x, which is 2 pi, the period of tan x is just pi. It repeats itself from pi over 2 to 3 pi over 2. So now we need to do a horizontal stretch by 3/2. Okay? The shortcut that we're going to use for tan is to label our asymptotes first. If we're going to multiply our x values by 3 pi over 2, and our asymptotes are currently at x equals negative pi over 2, x equals pi over 2, and x equals 3 pi over 2. If you took each of those, I'll draw my new grid here, and I multiplied by 3/2. Can you see that this first one, 3/2 times negative pi over 2 will be negative 3 pi over 4. And the second one, will be at 3 pi over 4. And finally, if I did do that next one, 3 times 3 is 9 pi over 4. And here is our new graph. And our new graph has a period. If the period was pi, and we multiplied by 3 over 2, our new period is 3 pi over 2. The over 4 is because let's take our first asymptote, which is negative pi over 2. And if we're multiplying our x values by 3 over 2, how do I multiply fractions? I multiply the tops. That will give me negative 3 pi. I multiply the bottoms. That will give me 4. So for our tan graph, we find out where our new asymptotes are going to be. And again, our period is what got changed. Your y values would still stay exactly the same where they were. And finally, in part C is dealing with a sign graph. We've got y equals sine, and it's x over 7. If you have x over 7, recognize that x over 7 is the same as 1/7 times x. And our sign graph, again, label your axes family. Here's our sign graph, starting in the middle, going up. Those middle, maximum, middle, minimum. There's our sign graph. And of course, our sign graph has a period, just like our cosine graph, of 2 pi. It takes a full circle to repeat itself. And here, we have a horizontal stretch. X's are liars. We multiply by the reciprocal. So we would multiply our x values by 7. So just like we did in our cosine graph, we're going to think about, well, if one full period was 2 pi, and I multiply by 7, does it make sense that that final mark will now be at 14 pi? It's now at 14 pi. And just like your normal sine graph to graph it quickly needs to be in 4 sections, we now take this and divide it into 4 sections. And these aren't hard to label. I always start with the middle one, because it's pretty easy to cut something in half. Half of 14? 7 pi. Then I do the first one. Half of 7, you could either write 3.5 or you could leave it as a fraction. 7 pi over 2. And then once you know the first one, does it make sense that the third one is just 3 of the first one? If one of them is 7 pi over 2, 3 of them, multiply that 7 pi over 2 by 3. I'll get 21 pi over 2. My amplitude, my A value, is still 1. So my amplitude stays 1. And a sine graph starts in the middle going up. So I start in the middle. Then I go up to my maximum. Then back to my middle. Then down to my minimum. And back to my middle. So the B value gives us a shortcut for our period. And if we can draw our period and divide it into 4 equal sections, we can graph it quicker than doing our regular transformations. So now we have a shortcut for our amplitude and a shortcut for our period. By the way, the period of this one is 14 pi. So now you can circle the rest of the questions, or is this not quite? No, I think we do one more to circle. In the end, you're going to circle all of 3, A, B, C, D, E, and F. But after this one, just C and D.